Good morning and welcome to this third lecture. So, today's topic is going to be residues. So, what is the residue of a holomorphic function at a singularity? So, here is the setting. We have a holomorphic function f, defined on an open set U, is our holomorphic function. And we have an isolated singularity. Z0 is an isolated singularity. And as we know, we can then write the Laurent series expansion for f around the singularity Z0. This will give us a Laurent series of the form, so f of z will be the sum, n goes from minus infinity to plus infinity, of some coefficients a, n, z minus z0 to the power n. And this Laurent series converges on, so this holds for every z in a punctured disk of radius, let's say big R, centered at z0, which is fully contained in U. Okay? So for every punctured disk contained in the domain, we get convergence of the Laurent series inside this punctured disk. So the residue of f at z0 is just the coefficient minus 1, a minus 1 of the Laurent series. So the residue of f at the singularity Z0 is, so we denote it by this symbol, res f comma Z0, and it's defined just as it's the coefficient a minus 1 in the Laurent series. In other words, it's the coefficient of the term 1 over z minus z0. And if we use, so what's special about this, this coefficient minus 1? Well, first of all, if we use the formula for the coefficients of the Laurent series, let me recall what the formula is, let me write it here above. In general, an is 1 over 2 pi integral over a circle around z0, so k z0 r. Here the radius small r is smaller than this radius big R, and here I should write f of z divided by c minus z0 to the power n plus 1 in dz. Okay? This is the general formula for the coefficients, and in the particular case n equals minus 1, this term is just 1, the exponent is 0, so we get the simple expression, so a minus 1 is 1 over 2 pi integral over this circle, k z0 small r, f of z in dz. Okay? So an equivalent definition for the residue. So the residue is either the coefficient of the term 1 over z minus z0 in the Laurent series expansion, or it's 1 over 2 pi, the integral of f, of the function f, on a on a small circle going around the singularity. So this is the residue of a holomorphic function at an isolated singularity. So what's special about this number? Well, one first fact is a fact that was actually asked as an exercise, the first exercise sheet you received. So it's an important fact, so let me restate this as a proposition. Here is the proposition. So let's say that we have a function f. We have our function f, or let's say we can also reduce the domain. It's defined on this punctured disk around Z0, radius r, values in C, and it's holomorphic. Then f has a holomorphic primitive on the same on this punctured disk, if and only if the residue of f at Z0 is 0. Okay? So the residue is the obstruction for f to have a holomorphic primitive on the whole punctured disk centered at Z0. So let me recall some things. So before we show the proof of this proposition, let me recall some things about primitives. So first of all, what is a primitive of a holomorphic function? A primitive of a holomorphic function is just another holomorphic function, let's say big F, whose derivative is small f. This is a primitive of small f. And the other important thing is whenever we have a curve in the domain of the domain of our primitive big F. So let's say that we have this factor, let's say now in general, on some domain U. So the holomorphic function small f is the derivative of another holomorphic function big F, and both are defined on the open set U. Now let's say that we have a curve gamma in U. As usual, this was smooth. Then in this case, the integral of the function small f dz along this curve gamma is just the difference of the values of the primitive big F at the two endpoints of the curve. So it's f of gamma b minus f of gamma a. So in particular, if small f admits a primitive, then the integral is 0 on all closed curves. So in particular, this integral is 0 for all gamma closed curves. Because here the endpoints coincide, and so these cancel each other. And so whenever a holomorphic function has a primitive on a certain domain, then its integral on every closed curve will be 0. And not every holomorphic function has a primitive on its domain. The typical example that you already know is if you take the function f of z equal 1 over z. This is a holomorphic function on C minus the origin. But on C minus the origin, this holomorphic function has no globally defined primitive, and the reason is that if we integrate 1 over z on a closed curve here, which goes once around the origin, for instance, we can take k01, this is the circle of center 0, radius 1, going once counterclockwise around the origin, then as you know, we obtain 2pi. This is different from 0. We are integrating 1 over z over a closed curve, and we are obtaining something non-zero. So the function small f cannot have a primitive on C minus the origin. So the function small f will have primitives. This is how you define the logarithm, the complex logarithm, but you cannot define the complex logarithm over the whole C minus the origin because of this fact. Okay, after this, after recalling these known facts, we can now prove this proposition. So, proof. Let's deal first with this direction. So let's assume that f has a holomorphic primitive. Then if f has a holomorphic primitive, so let's assume that f is the derivative of big F on this puncture disk. Well, then in this case, the residue of f until naught. So we said one definition of the residue is 1 over 2pi integral over a circle around z naught, k z naught r. Here small r is a number which is a positive number which is smaller than big R, f of z in dz. But we just said that when the function small f has a primitive, then the integral on each closed curve is 0. So this has to be 0. Okay, so when we have a primitive, the residue has to be 0. Conversely, let's assume that the residue is 0. In other words, we are assuming that if we write down the Laurent series expansion for f around z naught, we obtain something of the form an z minus z naught to the power n. But this sum ranges over all, let's say, over all integers, but n is, you can write n different from -1. Because the coefficient a minus 1 is not here, it's 0. Because we're assuming that the residue is 0, and the residue is exactly the coefficient a minus 1. So this is our Laurent series expansion of f, and it converges on this puncture disk centered at z naught. And now, using this expression, we can explicitly write down a primitive for small f on the same puncture disk. The primitive, we just integrate term by term. The primitive, we define big F to be the sum n z n different from -1. Here we have an divided by n plus 1 times z minus z naught to the power n plus 1. Okay? So this series, first of all, is well defined because here we're excluding n equal minus 1, which would be exactly the problematic term because here we see a denominator n plus 1, which of course has to be non-zero. So this is a well-defined series, and it's obtained from this series, and you can check easily that since this series was converging on this punctured disk, the same is true also for this series. This is also converging on that punctured disk. And moreover, if you differentiate big F, you obtain exactly small f. So this is the desired primitive of small f. Okay, so the residue is the obstruction for a holomorphic function to have a primitive around the given singularity. So we said that one of the two equivalent definitions of a residue is given by integrating f on a small circle around the singularity. So by this we obtain that, so again, when we have f defined on this punctured disk, centered at z naught, bounding C, and it's holomorphic, then the integral of f z dz on any circle in this punctured disk going around the singularity, so let's say circle z naught r with r between big R and 0, this integral is precisely 2pi times the residue of f at z naught. Right? Because the residue of f at z naught was 1 over 2pi times the integral. So we have this identity. So this identity actually has a generalization to a more general situation in which we integrate over a contour which surrounds a certain number, a finite number of singularities of the holomorphic function f. So this is an important theorem. It's called the Residue Theorem. And here is a possible statement. So we have a holomorphic function f defined on its open set in the open domain U, holomorphic. Then we have gamma, a contour in U. Okay, so a simple closed curve piecewise smooth contained in U. And let's assume that the interior of gamma, was just, we said this is a simple closed curve in the plane, so it bounds a bounded region. This is what we denote by I gamma. This is the bounded region bounded by the contour gamma. So we assume that this interior is contained in U union a finite number of points, which will be isolated singularities for f. So it's U union z1 zk, where the zj's are distinct points, so pairwise distinct, isolated singularities. In other words, we are considering some contour. Contours are always parameterized counterclockwise. The contour itself is fully contained in the open set U, and the interior not necessarily, because there are possibly finitely many points, Z1, Zk, Z1, Z2, and so on. These are singularities for our holomorphic function, so therefore they do not belong to the domain of our holomorphic function. Okay, under these assumptions, then, the integral of f of z dz over this contour gamma is 2pi, the sum over all j going from 1 to k, over all the singularities of the residue of f at the singularity zj. Okay? So this theorem generalizes this formula. Now we're integrating not necessarily on a circle, we're integrating on any contour, and in the interior part of the contour we have finitely many singularities, and they contribute to the value of this integral. More precisely, the integral is 2pi times the sum of the residues at all the singularities. Okay, let's prove this theorem. So, proof. So we shall consider the Laurent expansion of f around the singularity zj, and more precisely, we will denote by hjz be the principal part of the Laurent series expansion around zj. So this ajz, this is a sum of the form n goes to 1 to infinity, so it's a principal part, so it's something of the form a minus n, and I'll put now also an index j, because we actually have j of this Laurent series, one for each singularity, so we have k of this Laurent series, and they are parameterized by the index j, z minus zj to the power n. Okay, so let this series be the principal part of the Laurent series expansion of f around the singularity Vj, and this for all j going from 1 to k. So we have k such functions. Okay, this function converges, so this series defining hj, the series converges on, each of them converges on C minus the point Zj. No? We recall that so a series of this form, this is a power series in 1 over Z minus Zj, will converge in general outside some disk, but here we were assuming that Zj was an isolated singularity, so we had convergence, the radius of this disk is actually 0, so we have convergence for all Z different from Zj. So the principal part will converge here. It's a regular part which instead could converge on a smaller disk. And so the whole Laurent series maybe doesn't converge here, but the principal part does. And therefore, we can define a new holomorphic function on the same domain, on U. We define G from U to C as G of Z is, we consider F of Z, and we subtract the sum over these functions Hj for j going from 1 to k. Okay, this is of course holomorphic on U because F is holomorphic on U, and each Hj is holomorphic on C minus Zj, and this set contains U. So this is holomorphic on U, but now the singularities at the points Zj are removable for G. So Zj is a removable singularity for G. And the reason is that if we consider the Laurent series expansion around Zj, so here we will get the Laurent series expansion of F, and the Laurent series expansion of F will contain as principal part exactly Hj, but here we are then subtracting all these sum of Hj, so in particular we are subtracting Hj, so we are killing the principal part of this Laurent series expansion around Zj, and so what remains is just a nice holomorphic function. We will get the regular part from here, and then we get also all the other Hi with I different from J, and these are nice holomorphic function far from Zj. Okay, so by this trick of subtracting all these principal parts, we now obtain that the singularity at Zj is removable. So we can remove it, and we obtain that now G extends to a holomorphic function. It's holomorphic on U, but also union these points, Z1, Zj. And therefore, when we integrate G over the contour gamma, we obtain 0, right? Because now the interior of the contour is completely contained in the domain of the holomorphic function G, since the domain of holomorphic function G contains also the singularities. Okay. And now we can just, so we know that this is 0, but we also have this identity, so we will now express this integral using this identity. And this will lead to the result. So, what we just proved is that the integral over gamma of G, Z is 0. But this integral is also the integral over gamma of F, dz, minus the sum J goes from 1 to K, integral over gamma of H J Z dz. What is this? This is the integral over gamma of f of z dz plus, minus sum j from 1 to k. So here we are integrating, so here we have this function hj, which is holomorphic except at the point zj, and this is a contour which goes around zj. So we can deform by this contour, and the integral we get is the same as the integral, for instance, on the circle with center zj and radius whatever we like, for instance 1 of hjz dz. Okay? Here we are using the fact that precisely stated, the curve gamma and this circle are freely homotopic in the set C minus Zj, and therefore the integral of this function, which is holomorphic on C minus Zj, on these two closed curves are the same. But this integral we know its value. This was the principal part of our function at Laurent series expansion at Zj. So this integral is just, so here we still have a sum j from 1 to k. This integral is just 2pi times this number a minus 1, the coefficient minus 1 of the Laurent. I put a j because this is the Laurent series corresponding to the singularity Zj. And this is nothing else but the residue at Zj. So this is, we can rewrite as integral of f of z dz. This 2pi, we can take it outside the sum, and then we have the sum j from 1 to k, and this is the residue of f at Zj. Okay? So the fact that this quantity vanishes, it's written here, tells us exactly that the integral of f is 2pi times the sum of the residues. So we've proven the residue theorem. Okay. So in the next lecture we will see that this theorem gives us a powerful way of computing integrals, also non-trivial integrals. But in order to apply this theorem to compute integrals, one needs to know how to compute residues. So how do you compute the residue of a holomorphic function at some isolated singularity? So let's start with the simplest possible situation, the case in which Z0 is a simple pole of F. In this case, I claim that the residue of F at Z0 is just the limit for Z going to Z0 of Z minus Z0 times F of Z. Okay, so you can compute the residue just by computing a limit. So why is this so? So proof of this formula. So this is a simple pole of F, so it's a pole of order 1. What does this mean? This means that F of Z is of the form A minus 1 divided by Z minus Z0. Okay, this is the part contributing, giving us the pole of order 1, where this number A minus 1 is precisely the residue of f at z0, and we are assuming that this is a simple pole, so this number is non-zero, plus some holomorphic function, g of z, where g is holomorphic on some disk radius r around z0, and some full disk now, including the center z0. Okay, this is just because at a simple pole we do have, so this is just the Laurent series expansion at a simple pole. We just have this term of degree minus 1 plus a holomorphic part. Then, if we multiply everything by z minus z0, so z minus z0 times f of z is a minus 1, which is the residue, plus z minus z0 times g of z. And then if we consider the limit for z going to z0, this converges to, this goes to 0, because this goes to 0 and this is holomorphic on the whole disk, so this will just converge to g at z0, which is a finite complex number, so everything converges to a minus 1. So the value of this limit is the residue, and this is a limit for z going to z0. Okay, so this is the formula for computing the residue at a simple pole. And you can use this formula to compute our first example. In our first example, we will, here is the example, we want to compute the integral of the function sine of pi z divided by z squared plus 1 dz. This we want to compute on a circle centered at 0, radius 2. Okay. So, what can we say about the function we want to integrate? F of z equal sine of pz divided by z squared plus 1. So z squared plus 1, so the zeros of this polynomial, z squared plus 1, are the square roots of minus 1, so they are I and minus I. So this is just sine of pz divided by z minus I times z plus I. And this formula shows that this function f has two simple poles at I and minus I. And here we are integrating, we would like to integrate this function on a circle of radius 2, centered at the origin. So here is the circle of radius 2. And the two poles at I and minus I are contained, this is I and this is minus I. So they are both in the region which is bounded by our contour gamma. So in order to compute, the value of this integral will be precisely 2pi times the sum of the two residues here. So we have to compute these two residues. And we use, so we have simple poles. So to compute, for instance, the residue at I, we multiply our function by z minus I, thus obtaining sine over sine of pz divided by z plus I, and then we take a limit for z converging to I, and we obtain sine of pi divided by I plus I to I. Okay? And here actually you can use also the formula, so sine of I times a complex number z, this is the same as I sine hyperbolicus, hyperbolic sine of z. Okay, you can check the validity of this formula. And so if we use this, this is nothing else but sine Iz, this is I is just sine hyperbolicus. So we have an I in front, so it's sine hyperbolicus of p divided by 2. Okay. So this means that this number here is precisely the residue of f at I. Then you do a similar computation for minus I, meaning that we now multiply by z plus I, f of z. This time we obtain sine over pz divided by z minus I. And now we let z converge to minus I, and we obtain sine of minus pi divided by minus 2i. Sine is an odd function, so this minus comes out and simplifies with this minus, and so we get the same result. Sine hyperbolicus of pi divided by 2. So the residue at both singularities is sine hyperbolicus of pi divided by 2, and therefore the value of this integral is 2pi times the sum of the two results, so times sine hyperbolicus of pi. We obtain this formula. Okay. So this was the computation of the residue at a simple pole. So what happens if we have a pole but of higher multiplicity? Here we also have a formula, a bit more complicated, not that much. So let's assume now that Z0 is a pole of order, say at most k, let's recall than k. It could be k, but it could be also lower. The formula will hold nevertheless. Okay, we take a pole of order lesser or equal than k. Then the residue of f at Z0, you can compute it in this way. It's 1 over k minus 1 factorial times the derivative being dz. Derivative, we derive k minus 1 times, and we derive the function z minus z0 to the power k times f of z. And this will derivative we compute at the point z equal z naught. Okay, so what you have to do to compute the residue is you consider this new function, you multiply f by z minus z naught k, where k is at least a multiplicity, possibly bigger. Then you take this function, you derive it k minus 1 times, you evaluate this derivative at the point z naught, and finally you divide by k minus 1 factorial. Okay, why is this so? Again, this follows from the formula from the Laurent series expansion of f at z naught. So, f of z, since this is a pole of order less or equal than k, the expression, the Laurent series expansion, starts with minus k, and then goes to plus infinity, and here we have again z minus z naught with me. Okay, we have no indices less than minus k because the pole has order less or equal than k. And then when we multiply by z minus z naught to the power k, we increase here this power by a plus k, and by shifting the indices, we can rewrite it as a sum. Let's say m goes from 0 to infinity, and here I can write a n m minus k z minus z naught to the power n. Okay? So now, so this is as it should be, since the single pole was order less or equal than k, this is now the sum of a genuine power series. And now in this genuine power series, we would like to isolate the coefficient which is interesting for us is the coefficient a minus 1. So when is m minus k minus 1? M minus k is minus 1 exactly when m is k minus 1. Okay, so we are interested in the coefficient of the power of the monomial z minus z naught to the power k minus 1. So in order to extract this coefficient from a power series, the usual way is to compute derivatives and then evaluate the precise derivative at z naught. So if we want just to extract the coefficient of z minus z naught to the power 0, we would just evaluate this function at z naught. If we want to compute the coefficient of z minus z naught to the power 1, we would compute one derivative and compute it at z naught. Here we want to compute the coefficient of z minus z naught to the power k minus 1, so it means that we have to compute, so a minus 1 is given by computing, or maybe let's write like this. If we derive this k minus 1 times d in dz k minus 1 of this function, z minus z naught f of z, what is this kth derivative? This is sum m goes from 0 to infinity. So here we're deriving k minus 1 times, so this sum will actually not start with 0, it will actually start with k, also with k minus 1, and here we will get a m minus k times, if we derive k minus 1 times, we obtain an m times m minus 1 up to dot m minus k minus 1, so m minus k I should write plus 1 and then another plus 1, so plus 2 times z minus z naught to the power, we have derived k minus 1 times, so m minus k plus 1. Okay, you can easily check this formula. And then if we evaluate, so this is the derivative at any z, if we evaluate it at z equal z0, what we obtain is exactly the term here where the coefficient here is, where the exponent is 0, so when m is k minus 1, and we obtain that this number is then precisely m is k minus 1, so we obtain k minus 1 factorial from here times a, when n is k minus 1, this is a minus 1. Okay, so the value of this k minus 1 derivative at z naught is precisely k minus 1 factorial times a minus 1. So our a minus 1, the residue, is this derivative divided by k minus 1 factorial. Okay. So we have this formula, this general formula for computing the residue at a pole. So example. As an example, let's again compute an integral. This time I will compute the integral of the function integral dc z squared plus 1, but here I put a square on the curve gamma. And here as gamma I will take a half circle like this. Here is the origin. This is a half circle of radius big r. For some r here is big. It should be, say, at least 1. Okay, we have this half circle. We want to compute this line integral. Again, the function f of z is, so the function 1 over z squared plus 1. This has two poles at I and minus I. This we can rewrite it as 1 divided by z plus I squared this time, z minus I squared. So we have two poles at I and minus I, and one of them is interesting for us, the pole at I, because this is inside the region bounded by the contour. The other pole is outside, so it will not enter in our computation. So we need to know the value of the residue of f at I. And now I is a pole of order 2 of our holomorphic function. Here we have z plus I to the power, here, z minus I to the power 2. So I is a pole of order 2. So what's the recipe for computing the residue at the pole of order 2? We have to define a function. We have to multiply our function by z minus z naught to the power k minus 1. Now k is 2, so just to the power 1. So we multiply, and z naught is I. We multiply our function f by to the power k, so to the power 2. So we multiply our function f by z minus I squared, thus removing the singularity, and we obtain 1 over z plus I squared. And now we have this function, and we have to take the derivative order k minus 1, so the first derivative of this function. What is the first derivative? The first derivative of this is minus 2 divided by z plus I to the power 3, and then the residue of f at I will be, according to the formula, k minus 1 factorial, but k is 2, so k minus 1 is 1, 1 factorial is 1, don't write it, times the derivative of g, the first derivative of g, at the point I. Therefore, we get minus 2 divided by I plus I is 2I to the power 3. And this is, this 2 gives us an 8, with this 2 we get a 1/4, and I to the cube is minus I, but it's in the denominator, and 1 over minus I is just I, so we have I over 4, and there is still a minus in front, so it's minus I over 4. Okay, this is the value of the residue, and then you can use the residue theorem and say that then the value of this integral is 2pi times the value of the residue, so times minus I over 4. So we get I times minus I is plus 1, so we get p half. This is the value of this integral. Okay, so computing the residue at a pole, especially if the order of the pole is high, is a bit more complicated because we have to compute then more and more derivatives. And so let me conclude with another example showing that in many cases, instead of using the formula, it's better to actually directly find the relevant part of the Laurent series expansion, and from there read the residue. So the last example for today is, the exercise is to compute the residue at 0 of the function f of z, which is 1 over z squared times sine of z. Okay, we want to compute the residue at 0 of this function. So here 0 will be a pole of order 3. Now here we have z squared, and sine z has a simple 0 at 0, so we get another multiplicity 1 from here. So in total will be a multiplicity 3. And so we need to compute the relevant part of the Laurent series expansion, and for this we can use the power series expansion for sine. We know that sine of z is z minus z cubed divided by 3 factorial, so divided by 6, plus what remains is a big O of z to the 5. And if we use this formula, we get that f of z is, instead of this, let me write in this formula. Let me write, so it's 1 over z squared times sine to the power 1. So let me write z minus z to the cube over 6 plus big O z to the power 5, everything minus 1. So here we can isolate a z and take it out, but since there is a power minus 1, this will contribute, giving us 1 over z to the power 3. And inside we have divided by z, so we have a 1 minus c squared divided by 6. And here we remain with a big O of z to the 4. Everything to the power minus 1. And then we use, let me write it here. Also here we have 1 plus something small to the power minus 1. So we have something of the form, so 1 plus w, that w is small, to the power minus 1. Or if you want, it's 1 over 1 minus w. Plus w. Plus. What's the first order expansion for this? This we know. This is 1 minus w plus big O of w squared. Okay. This is just, you find it just by looking at the first terms of the geometric series corresponding to minus w, whose total sum is 1 over 1 plus w. Okay, so if we use this expansion here to express this term, what we obtain is 1 over z cubed, and here we obtain a 1. Then we should write minus this thing, so this minus becomes a plus z squared divided by 6 plus big O of z squared, or z to the power 4, sorry. And here then I would also have to write a big O of all of this to the power 2, but this is already included in this big O of z to the 4. Okay, so I got rid of this minus 1 just by changing the sign here. And here, of course, I don't need to change the sign because this is a big O, so it's in any case a function I'm not really writing down explicitly. Okay, but now from this expression I can read my Laurent series, or at least the relevant part of the Laurent series. So this starts with 1 over z cubed. This is the highest, say, negative power, corresponding to the fact that this was a pole of order 3. And then the next term will be 1 over 6 times 1 over z. And then what's next is this is big O of z to the 4 divided by z to the 3, so it's a big O of z. So this means that everything which is in here, this is something which is actually even infinitesimal for z going to 0, so this will contribute to the regular part of the Laurent series expansion, and this is the part we are not interested in. Instead, the coefficient, the residue is the coefficient of 1 over z, and so it's precisely 1 over 6. So here we have the coefficient of 1 over z to the power 3. This power 3 will correspond to the order of the pole, but the residue is the coefficient of the term 1 over z. So in our case, we obtain that this residue of this function at 0 is 1 over 6. Okay? So, being able to work with this Landau notation, with the notation of small o and big O, and knowing power series expansion of many functions, for instance sine, allows you to do these computations relatively easy without the need of computing many derivatives. Okay, that's it for today, and I wish you a good weekend, and then we will talk live next week. Thank you very much.